and you can see the some discussions I have written here. So, since any real process going from state 1 to state 2 must satisfy the Rayleigh line equation 5 and the Rankine-Hugoniot relation, okay, both should be satisfied. So, the points between B and C on the Hugoniot curve are not realizable because no valid Rayleigh line can be drawn. So, this is the first inference. Then for the upper branch of the Hugoniot, there is a limiting Rayleigh line. Okay. After that, Rayleigh line cannot be drawn as a tangent basically. So, that is a tangent. So, the limiting line is tangent to the Hugoniot curve at the point D, and this is called upper Chapman-Juggiot point. Okay. Or say we can also say Juget point, Juget, okay, Chapman-Juget point. So, this point D here is called upper Chapman-Juget. Sorry. Okay. So, CJ I will say CJ point, upper CJ point, and similarly here it is called lower CJ point, Chapman-Juget point. Okay. Okay. So, this it can be shown. No, I can show that Mach number will be 1 at this point D, upper Chapman-Juget point, Mach number will be 1. Points above D are difficult to observe in the lab scale experiment. Theoretically, it may be fine, they can solve the equation and get, but it is not practically possible to achieve this in the lab scale experiments. In some conditions, you may get it, some big engines etc. you may get it, but not possible. Similarly, there is a limiting Rayleigh line in the lower portion which will give the tangent to the Hugoniot, which is point E called lower CJ point or Chapman-Juget point here. Okay, so this point E. Okay, so this is accessible. C and below E is not accessible. It is not practical. Okay, theoretically you can get the values, but it is not practical. Strong deflagration and supersonic exit velocities. Okay, now let us see about the burnt gas velocity. Okay, so for that let the wave be moving. I will come out of the wave and see the wave propagating to the mixture. So, wave propagates, correct, at the VW. Okay. So, that means you can say VW is equal to the U1. So, when the wave is at rest, the velocity of the unburnt gas approaching the wave is U1. So, VW equal to U1. So, that is known. Now, what is V2 we are going to find. Okay. So, now V1, this is V1, VW, U1, all the things we can read here. So, let us say, so when I am in the laboratory frame of reference, what happens is the combustion wave is moving with the velocity of VW. Velocity of unburnt gas V1 is, see, this U1 was the velocity or at which the unburnt gas approached the wave. Now, if the wave is propagating, unburnt gas should be at rest. So, V1 is the velocity of unburnt gas which should be at rest when the wave propagates over that. So, that is equal to 0. Okay. Now, VW equal to U1, that is known. So, either the unburnt gas should approach the wave at the velocity of U1 or the wave should propagate at the same velocity towards the unburnt gas. Now, the velocity V2 is U1 minus U2. So, that is the thing here, U1 minus U2. So, we can say V2 equal to U1 minus U2 or minus of U2 minus U1. Okay. Now, I know the expression for U2 minus U1, that is what we have derived there and kept. So, the U2 minus U1 which we derived here, okay, that can be used here now. The minus m dot double dash square into 1 by rho 2 minus 1 by rho 1. So, now just to see the direction only we are doing this calculation. So, at point D, V2 is less than V1 here, point D. So, this is V1. So, this is V1 P1. Point D, V2 is less than V1, correct. So, when V2 is less than V1, this is V2 and this is V1. when V2 is less than V1, this is negative. Negative of negative will be positive. So V2 is positive. So for detonation, the burnt gas follow the combustion wave. When the wave moves in the positive x direction, the burnt gas also follow the wave. That we have to understand. For deflagration at E, point E, let us take here, point T, you can see that the V2, if this is V2 now, V1 is less than V2. V2 is greater than V1. So U1 is less than U2 or V2 is negative. So for deflagration, burnt gas flow in the direction opposite to that of the flame. Then we have to understand that. Now, estimation of detonation velocity. Okay, so at the upper Chapman-Jugot point, CJ point, velocity is sonic. Above D, the velocity is subsonic, and between B and D, the velocity is supersonic. When I say velocity, it is the approaching velocity. Please understand, this is the approaching velocity, not the burnt gas velocity. Burnt velocity is different, correct? We have already seen that. This is approaching velocity. So when you want to do this, the approaching velocity should be in between the B and D is supersonic. So the continuity equation I can write as rho 1 U1, the approaching velocity is U1, equal to rho 2 into C2. Okay. So now U1 equal to rho 2 by rho 1 into C2. What is C2? C2 is the speed of sound, which is nothing but gamma RT, root of gamma RT, C equal to root of gamma RT. So C2 is gamma R2 T2 power half. So this is the expression I get. Now I can relate this rho 2 by rho 1 and T2 to state 1 quantities or other quantities. Okay. Now for that I make an important assumption that P2 is much greater than P1. Okay. So when I say the momentum equation, P1 plus half rho U1 square equal to P2 plus half rho U2 square, for example. So now P1 is 0 because I can neglect P1 and consider the value of P2. So P1 is very low. So I write this equation. Please understand that I write this when I use this momentum equation, I can write rho 1 U1 square divided by rho 2 U2 square minus P2 by rho 2 U2 square. Just divide throughout by rho 2 U2. So I have to put 1 here, 1 and 2 here. Okay. So momentum equation. So P1 plus half rho 1 U1 square equal to P2 plus half rho 2 U2 square. By this assumption, I say P1 is equal to 0. So I can write this. From that I can get the value of rho 2 by rho 1 as this. Now U2 is equal to C2. So using that I can write rho 2 by rho 1. Then using the definition of this Cp etc. plus the equation of state P equal to rho RT, I can get a simple formula for rho 2 by rho 1 as gamma plus 1 by gamma. So you can just use it, very simple derivation here. So now similarly T2, I want a relationship for rho 2 by rho 1 which I have got now. Similarly I want a relationship for T2. So for that what I do, solving the energy conservation equation for T2, eliminating U1. Using the continuity equation, substituting C2 equal to U2, I can get this, and also using the density ratio. So much thing I do here. I am not deriving it. So that's what the summary is. So what I do here is, I know that Cp T2 plus half U2 square equal to Cp T1 plus half U1 square, correct? So that I try to now take a value of T2. So T2 equal to T1 divided through by Cp, okay, U1 square plus Q is there here, okay, U1 square minus U2 square by 2Cp plus Q by Cp. So the energy equation, this is only energy equation, simple. Now this you retain. Now we'll try to write this gamma RT. So U2 is C2 equal to root of gamma R2 T2, that you substitute, you get this equation. Now you know that gamma R2 by gamma minus 1 equal to Cp, correct. Similarly, P equal to rho RT. So, use this equation, finally this equation T1 plus Q by Cp plus this, here you have another T2. So, now this you have to take to this side and do some algebra, you get a simple equation for T2 as 2 gamma square by gamma plus 1 times T1 plus Q by Cp. Plus understand that this is a simple equation because we have assumed Cp to be constant, okay. So, now you use this density ratio rho 2 by rho 1 and T2 and get the velocity for detonation, that is all. So, detonation velocity is nothing but the approaching velocity u1 equal to 2 gamma plus 1 into gamma into R2 times T1 plus Q by Cp whole power half. Okay, now the above expression for detonation velocity is very approximate. First of all, main assumption is P2 is much greater than P1, and also we have the constant physical properties. Okay. Now slightly we can relax it. So what we will do, we will first assumption say constant and equal specific heats, say Cp1 equal to Cp2. Let us avoid this. When you do that, you get expression for state to temperature and detonation velocity slightly better, but still it is approximate. Okay, I can get slightly better values, but it is still approximate. This is the thing. So now I try to put, instead of considering Cp1 equal to Cp2, now I will consider it is not. So I will put the ratio of Cp1 Cp2 here. So T2 is slightly better. See, if you see this, you can get gamma. There is no gamma 1 or gamma 2. Now I specify it is gamma 1 or gamma 2. Okay, so please understand gamma 1 will be equal to Cp1 by Cv1. Gamma 2 will be equal to Cp2 by Cv2. Now, if I assume that Cp1 equal to Cp2 and Cv1 equal to Cv2, then gamma 1 will be equal to gamma 2. Okay, these are all the assumptions made here to get this. But when I relax that, at least this the constant specific and equal specific etc. for the products and this, if you relax, I will say I will take gamma 1 equal to Cp1 by Cv2, Cv1 sorry. Cv1 and similarly gamma 2 equal to Cp2 by Cv2. Now you can see that I will retain gamma 2 here and the ratio of Cp1 by Cp2 etc. here and get this, but still it is approximate, but slightly better than the previous equation, because I am now relaxing the constant property assumption here. So I get a improved equation for this ud. Okay, so this you can use. Okay, but please understand that more exact mathematical description of one-dimensional detonation wave. Please understand one more thing, detonation is not one-dimensional phenomena, it is 3D in phenomena. However, some assumptions can be made and one-dimensional detonation wave propagation can be adjudged. For that, you need a numerical solution, and NASA Chemical Equilibrium Code CEC as a module to do this. Okay. Now the last we will see at last we will see a worked example. Okay. A combustion wave propagates with a mass flux of 3500 kg per meter square second. Okay. And the initial mixture has a temperature of 298 Kelvin and 1 atmosphere pressure. Okay. The molecular weight and the specific heat ratio of the mixture burnt, and now both are same. Molecular weight is 29 kilogram per kilomole and specific ratio gamma is 1.3. So that is what is given in this. So that then the heat release rate Q is given as 3.4 into 10 power 6 joule per kg. So now determine the state of the burnt gas and determine in which region this state lies in the Rankine-Hugoniot curve. Then Mach number of the burnt gases. So this is the problem. Okay. Now let us use the equation of a Rayleigh line, equation 5 Rayleigh line. So P2 equal to P1 plus m dot square into V1 minus V2. Okay. So, similarly equation 8 is written like this, okay, equation 8, that is the Rankine-Hugoniot curve equation. Now, I want to fix the state. So, what is V1? V1 is R P equal to rho RT. So, R T1 by P1. So, I get 0.843 meter cube per kg, that is the volume 1. Pressure is 1 atmosphere, initial pressure is 1 atmosphere. So, initial state is fixed as 1 atmosphere and specific volume as 0.843 meter cube per kg. Now, P2, this equation, radial line equal to P1, okay, all the values, correct. So, you can see P1 plus m dot square, m dot given 3500, then V1 and V2, okay. So, V1, but I do not know V2. So, I form an equation for P2 in terms of V2 here like this, form an equation for P2 in terms of V2. Similarly, heat addition, this equation 8, that is the Rankine-Hugoniot equation. I can substitute the values here, but please understand, I do not know both P2 and V2, but I know now from this equation, radial line equation, I know P2 in terms of V2. So, P2, now substituting for P2 from the radial line equation, so you get a quadratic equation in V2, okay, and this is the quadratic equation. When I solve, I get two volumes, V2s, that is 0.723 meter cube per kg and 0.239 meter cube per kg. You can readily see that V1 was 0.843 meter cube per kg, and we got two V2s from the quadratic equation, both are less than that. That means we are on the detonation curve, correct. So, if you see the here, this is the initial point, but both V2s are less than this, no. So, either I will be here or here somewhere, correct. I am going to be there in these regions. So, both V2s are less than the V1, initial V1 what I got. Okay. So, now that is the two values I get. Now, for both you will try to fix the state. So, corresponding to the V2 of 0.723, P2 value is got as, this is say 1.57 megapascals. Similarly, for V2 of 0.239, I get 7.5 megapascals. So, obviously, you can see the higher, we are going traveling in that curve to a higher value of pressure. Okay. Now, the velocities are calculated. Now, I know the pressure, state 2 is fixed now, correct. Pressure for corresponding each state is fixed. Now, how will I calculate velocities? I know the mass flux, mass flow rate is what? Mass flow rate is rho AV, a mass flux is rho V. So, A divided by A, so rho into V. So, so this is rho, so rho into V, but rho equal to 1 by specific volume. So, capital V is the velocity, so velocity by specific volume. So, velocity will be equal to mass flux into specific volume. So, for specific volume of 0.723, velocity will be 2530 meter per second, state to velocity. For this V2 equal to 0.239, it will be 836.5 meter per second. So, I am getting two velocities, okay, 22530 for the specific volume of 0.723, which is slightly less than the initial 0.843. If it is much less than the initial, that is V2 equal to 0.239, pressure is very high. For that, I am getting a lower velocity of 836.5, correct. Now, I calculate the speed of sound gamma RT, okay. For that, I need temperatures, gamma RT, no, T I need. So, for each volume, again I calculate temperature as for 0.723, I get the temperature as 3963, and for 0.239, I get temperatures of 6253. So, now, so 6000 etc. I cannot realize in the lab scale. That is what we are trying to make a point here. It is not realizable in the lab scale. So, now from this I can calculate the value of the speed of sound A2 for 0.723 meter cube per kg, it is 1215 meter per second, and for 0.239 it is 1526. So, Mach numbers will be for the specific volume of 0.723, it is 2.08. that means supersonic. So, that will be in between the B and D value, correct, B and D, that portion, and this is subsonic, that will be above D. For 0.239 it is above D. So, both specific volumes are less than state 1. So, this state corresponds to subsonic velocity lies in the upper Cj point, okay, above the point D, 7.5 megapascal, 0.239, subsonic velocity 0.55, that is above that, above D, and this 1.57 megapascal, 0.723 meter cube per kg, that lies in the region between the points B and D because it has a supersonic velocity. Okay. So, you can see that a very high mass flux causes detonation. If they reduce the mass flux, etc., then you go to the deflagration part. Okay. So, I will stop here.